All right. Good morning. Of course, this is being recorded. And if you have any questions, kindly put it in the chat and I'll be stopping periodically to look at the chat. And same format as last week. This is Dr. Garias, MED 1105DAX. And it is today, Tuesday, August 11. What is due today? Task 1, discussion 1, lesson today. And again, as a quick reminder for those of you who just jumped on the call, kindly mute, and if you got any questions, put it here in the chat. So as a review, we talked about this thing and a similar picture, and also to share with you the rationale, like why are we doing chemicals like atoms and molecules? What does that have to do with anatomy and physiology? Well, if you look at this, and it's the hierarchy of the organism, if you're going to have a problem at the atomic level, it's going to cause problems in the molecular level. If you have problems in the molecular level, it's going to cause problems in the macromolecule level. Then it's going to affect the organelles, which are the things that make up your cell. And we're going to talk about that in the lecture next week. So you could see here, which chemistry is the way these atoms and molecules interact with each other. If there's something wrong with you at the chemical level, there's going to be a problem here. And that also makes sense because that's why you take general chemistry and especially biochemistry, because general chemistry deals with things that aren't living. Biochemistry deals with bio-life. And you could see at the lower level, if something's wrong here, then there's going to be something wrong here, 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 and it's going to progress. And that's why when I'm in the Department of Internal Medicine, so that's why when my patient already has a diagnosis, many times it's kind of too late. We're more about prevention, and we're more about dealing with things when they're small, rather when they're already multisystemic. It's affecting multiple systems, and the patient's already in trouble. So on that note, that's the rationale of why we're doing what we're doing, and why the first 3 weeks is kind of like a primer on biochemistry and chemistry and cellular molecular biology, which, by the way, if you're in graduate school, please don't take that course unless you really have to. It's really not easy, and it's not fun, and it talks about, it's an entire year of what we're going to be talking about in week 3, all the things that go on with the cell at the molecular level. So let's look at task 2 for this week, and the chemical basis of life. And now we know and understand that chemicals and atoms are the basis. Atoms and molecules, which are even smaller than the building blocks of cells, they are the basis of why you're living. And all of these things require energy. And the second you don't give it energy, that's when you die. And then that's when everything starts falling apart. So there's a chemical basis. And if you're watching these videos, they talk about, did you ever wonder why when you jump in the bath, you just don't fall apart? When you're walking around, you just don't simply fall apart. But again, like we stated, if there's something wrong with something on the atomic level, right? And these are atoms. And let's look at what a typical, before we start talking about bonds, let's look at the smallest thing, which is an atom. Now you have this chemistry tutorial here on task 2. And this is the step 2 here. Now, those of you who are new to the course, and maybe some of you registered late and you're coming in, make sure to look at your announcements and watch the previous videos. And when we go over items and regarding things that you have to do to obtain credit, like for example, it says step 2, test yourself on the 13 problems. Well, and it goes, that's not the task that's due for next week. What's the task? You're going to submit a concept map and I'm going to talk about that momentarily, or maybe a little bit later in this morning's lecture regarding these concepts. So we're going to talk about basic structures, macromolecules, bonding, and water. So you should have four main ideas that are somehow connected together. And also remember, don't have to do the lab in the Carolina lab book, but the Carolina lab books have these wonderful notes that are in there as well. So let's look at this chemistry tutorial. No, that's not working for us. Let's not look at that. The Carolina notes have these really cool notes here. So, and that's protein starch test. Let's talk about, I mentioned that all of this requires energy. And yeah, so whoever designed the website, sometimes they mistyped it. But another thing you could also do is, hey, Google is a, and also, or give me a call. I could have an alternative link. But let's talk about how energy is required for everything. Now, this is the reason right here why we eat. So if you see, you have reactants and then products. And then of course, with also products, you also have byproducts, and that's the waste. So think of the reactants are like, why are the things that I'm eating? And the things that I'm eating have to be metabolized or somehow changed so that I can get my product. Now, typically the two main products that we're typically talking about that will lead to energy is oxygen and glucose. Glucose is a 6-carbon sugar. Now, not everything that we eat is sugar. There's all these different types of molecules that we have that we eat, but they have to be broken down. And in order for them to be broken down, it has to go through a chemical process. And this process costs. It costs energy. Now, if we didn't have this thing called an enzyme, which is a protein that will lower this energy, and this energy is called activation energy. So you have to see it in terms of, it's like riding a bicycle up a hill. Which hill would be easier to climb? It would be the lower one, obviously, right? So another way to think about it in this aspect is, for example, if you took a cheeseburger, maybe not one from McDonald's, but maybe one that you cooked, it takes a couple of weeks. If I left it outside in the air, it will take a couple of weeks for it to start to disintegrate. But I don't have a couple of weeks. I have hours for me to get it from reactants to products. So we have these things called enzymes in our body, and they catalyze chemical reactions, meaning to say is they lower the activation energy so that the metabolism or the change from reactants to products goes faster. And how do you know something's an enzyme? Well, it's going to have the suffix ASE at the end of it. So for example, I want to break down carbohydrates, that would be an amylase. If I want to break down a protein, that would be a proteinase, right? If I want to break down fats, that would be a lipase. And that is the real reason why we eat. And people who say, oh, I got to get rid of, those fad diets, like, oh, we can't have proteins in our diet, then how do you get enzymes? I need these, right? So, not necessarily meat byproduct, but it has to be a protein byproduct. And there's several plant options for those of you who are interested. So that's what an enzyme is. It breaks down things and it makes it faster and it drops the activation energy. And the less energy that you use, the more efficient that you'll have with products, right? Now, the main products, remember, is oxygen and a 6-carbon sugar, glucose. But everything extra, like for example, like if I eat too many proteins, I'll have extra nitrogens. I don't need that many nitrogens. I just need enough to make enzymes, enough to make proteins. And those would be anything that's extra would be a byproduct and would be waste. Okay. Again, carbohydrate, an example of an enzyme is amylase. Protein, an example of enzyme that breaks down proteins is called a proteinase. And an example of a general enzyme that breaks down fats is called a lipase. All right. Now, as you see here from the medical terminology, that the enzyme and the thing that it breaks down is called the substrate. It is highly specific. And this specificity, also known as the lock and key analogy, is the basis of modern pharmacology, and it's also the basis on neurotransmitters. It's the basis on why. Did you ever wonder, like when you take a medication, how do you know how does the medication know where to go? Well, because chemically, the substrate has to look and be attracted to the enzyme like a lock and key. And it's also the same thing for hormones. How do you know where the hormone goes and what's it attracted to? Because it's a lock and key mechanism. And if they don't fit perfectly, then the products won't be released. So for example, let's say, for example, this particular hormone, substrate, fits onto the enzyme, and then it produces a product that will make you depressed, okay? Or will decrease your dopamine or decrease the hormones and neurotransmitters that'll make you happy. So we'll take a drug that looks like the substrate and do what? You put it right in here and it blocks it. Like I stated, this is the basis of modern pharmacology, and it's also the reason how you know how things match up. So it's kind of like Lego. Now, the bad thing about this is there are certain diseases and there's certain chemicals that have a greater affinity to the enzyme substrate complex than its original intent. For example, we talked about happiness, and norepinephrine and epinephrine are the neurotransmitters that deal with happiness, and it also deals with euphoria, which is, just a fancy term for saying, that feeling you get when you get high. The problem is that the drug, for example, crack cocaine, has a 100 times more affinity or stickiness to the enzyme that creates the products of happiness and euphoria. So now you can see how difficult drug abuse is because now you have a foreign substrate, something that's not from within the body, now is stronger than the natural, that the natural drug in your body. And also knowing and understanding how this works could also give your patient strategies on how to deal with things. For example, we have over 250 million Americans on antidepressant medication. Recent study was done by American Psychiatric Association. It's not recent, it's about 10 years ago. They found out that regular exercise releases the same hormones, releases the same neurotransmitters, right? So why would you take these expensive medications that have so many side effects when all you need to do is get on a treadmill? But again, most patients don't want to get on the treadmill. They'd rather get the pill and in about 6 weeks be happy, right? But again, substrate and enzyme have to be a lock and key fit. Now, another thing that affects this lock and key fit and affects the balance of all the processes and chemical processes is pH. Now, what is pH actually? Let's look at a typical pH scale. Now, pH actually means the negative log of the concentration of the hydrogen ion. That's fancy schmancy, and that would explain the true meaning of what this scale means. But let's look at it from a layperson's perspective, and then we'll look at it from the chemical perspective. So what does pH really mean? It's a scale from 1 to 14, right? Not, I don't know, you can have 0, but that's crazy. It's more like 1 to 14, where 7 is balanced. 7 is neutral. 7 is water. And we know water as H2O. Okay, so let me take this scale and then expand it. I can take this picture and I could do this and I could put it here. Okay, so let's look at it. And what exactly does pH mean? pH really means the negative log of the concentration of the hydrogen ion. And what does that mean? Right? Hydrogen ion, if you got a lot of it, that means you're an acid. Now over here, all the way on the other side, so everything here from 6 to 0 or 6 to 1 is all an acidic. That means it has a lot of hydrogen ions. And if you remember anything from your high school chemistry, ions are charged particles like this, right? Has a plus. That means it has one less electron, and it is means it's highly reactive. Now on the other side, and the alkaline side, also known as your basic side, so you have acidic and you have acids and you have bases. And alkaline side, well, they have the hydroxide ion, which is equally reactive, but the exact opposite of the hydrogen ion. So an acid is just a chemical that has way too much H pluses. And a base or an alkaline is a chemical that has way too much OH minuses. Now, remember we talked about how we want to be in the middle, homeostasis? Human beings are around what, 7.4? And guess what? We're made out of 2/3 worth of water. So that makes sense. We should be neutral. And look what happens if I take H plus OH minus, that equals H2O. 2 hydrogens and an oxygen. Guess what H2O is? It's water. So that's where we want to try to be. We want to be balanced around here somewhere, right? And that's your pH scale. Now, in your pH scale, if you're not in balance, if you're too acidic, the acid's going to start reacting with the metabolism and those the enzymes and those chemical reactions that we talked about earlier, and it's going to mess things up. And on the other side, if you're too basic, it's also going to mess things up. Okay, so let's look at some examples of things that are a little bit more acidic. So, for example, tomato and coffee and vinegar and lemon, it's a little bit more on the acid side. So if you already have like some acid reflux disease or GERD, which is gastroesophageal reflux disease, you already got like severe heartburn. Should you be drinking coffee and eating pasta with tons of tomato sauce and homemade lemonade? These are things that will exacerbate your problem and will make you more acidic and will increase your hydrogen ions. Now, if you look at here, stomach acid, you may ask the question, then Dr. Grice, then why is stomach acid one of the most powerful acids right next to battery acid? Well, it's because the stomach is lined with mucus, which protects the stomach lining so that the acid doesn't just burn a hole right in your stomach. But what happens when you're stressed out or when you're immunocompromised and then you're eating and drinking too much of this stuff, right? Especially coffee. I used to drink like 10 cups a day until second year medical school. I got an ulcer. That's when the mucosal lining of your stomach starts wearing away. And then what happens? The acid bores a hole in your stomach and it causes a significant amount of pain and reflux and all this bad things. So what I had to do, I had to cut coffee out of my diet. And then it's a stimulant, so it's really not good for your blood pressure either. Now, let's look at the exact opposite. Ammonia and bleach and drain cleaner. That's OH minus. If any of you ever like get exposed to this stuff, you know that's highly toxic and it will react with your lungs. It will react with your eyes. And that's why, you know, especially if you put these two bad boys together, create a nice little biohazardous experiment. I once did that as a medical assistant. I put two of these things together. We had to evacuate the office. It was just not fun. And what did it do? It started reacting with everyone's eyes. It started reacting with everyone's lungs. Everyone started coughing. So you could see how it's not being on either extreme. Our body doesn't like it, nor does the vital metabolism reactions. And remember the word metabolism. Meta means change. Bol means growth, because that's what we're doing. When I eat, well, I didn't eat I would have liked to eat a sausage. What did I eat this morning? I ate oatmeal, right? Which is nasty when you just eat it regular, but it does wonderful things for your cholesterol. So I ate my oatmeal. My body doesn't really want the oatmeal. It wants only what? The oxygen that I was taking in as I was drinking the oatmeal. The oxygen derived from the water from the that I drank, and the water content of the oatmeal. It goes, and the breakdown of the carbon, hydrogen, and oxygen in the carbohydrates within the oatmeal itself. Right? It didn't want the other things, and the only way that that can occur is if I'm in balance. So what happens when you're not in balance? Well, when you're not in balance, there are things called buffers or buffer systems. Buffers are either weak acids or weak bases. Base is another word for base is alkaline. Weak acids or weak base that pushes you. So let's say I'm a little bit on the alkaline side or basic side. I'm around here. So I have a system in my body that's a weak acid that will push me back to where? Around 7. Or let's say I'm a little bit acidic, right? I'm a smoker, I'm a coffee drinker. I'm going to be a little bit acidic. So I'll have a weak base that will do what? Push me towards the middle. And maybe you've heard of some of these examples. Ringer's lactate. And lactate, if you see ATE at the end of a word, that's lactic acid. And another example is sodium bicarbonate or sodium bicarb. So Ringer's lactate is a weak acid that gets released from your body when you're a little bit over here. So it'll bring you back to neutral. 7.4 is the optimal pH for a human being. Or let's say I'm a little bit acidic. My body, specifically your kidneys, will start creating sodium bicarbonate, and it'll start doing what? Pushing you back towards the middle. So what kind of questions could come out on a midterm or an exam? I could ask you, okay, what's water? Should be where? Neutral pH. What does neutral pH look like? Here. What does drain cleaner or bleach look like? Alkaline, 13, 14, very alkaline. What does battery acid and stomach acid look like? Around 1, okay? What's a weak acid? Milk, right? Blood is a little bit on the basic side, or can be, okay? And what are buffers? They're weak acids or weak bases, right? Weak acid in the case of Ringer's lactate, and a weak base, which is an example, is sodium bicarbonate. And any of you who ever work in the business, when we put a line in our patient and I get a quick pH, right? A stat pH from my patient, I can now, when I put a line, I can now put a specific solution to do what? Get my patient back to normal. Okay, so that's the pH scale, and that's how that works. And remember, if the formula is too far to the left or too far to the right, you have an imbalance, and it then causes problems. And I'm going to give you a little bit preview from some of your nursing stuff, and also preview of anatomy and physiology at the end. I think week 10, we start talking about another way. So buffer is a chemical way to create the balance. Another way that we create balance is a respiratory compensation. Now, let's take Ringer's lactate as an example, okay? When, or lactic acid as an example. And here's an example of respiratory compensation. When you're not working out, we're just sitting here on our lecture. We're a nice pH 7.4. We're good. We're here in the middle. But let's say an emergency happened, building's on fire, I don't know, someone let a loose pit bull in the lab, and we're all running for our lives. So we're running around, right? What happens when you run? Well, your muscles use up the energy that we talked about, the glucose and the oxygen, and it makes ATP called, which is adenosine triphosphate. And we're going to talk more about ATP next week when we talk about the cell. But one of the byproducts of your muscles is lactic acid. Okay, so what happens? You have a buildup of lactic acid because you're utilizing your muscles. We're scrambling, we're running, right? And what happens when you start running? You're going to start breathing hard, right? Because we're running away from this this imaginary pit bull. So all of you who work out, you know that when you start running or start doing any cardiovascular exercise, it starts getting crampy. That's the effect of the lactic acid. You're going to start to having lactic acid buildup, and then you're going to start breathing heavily. So this is what happens. You start building lactic acid. What happens? Your pH is going to start to move what? From 7.4 to like 6 to around 5. And then what are you going to do? You're going to start breathing more. And when you breathe more, you start throwing out hydrogen ion. So when you increase your breathing, now it's going to push you back towards neutral. Now, don't you think we can do the same thing with a mechanical ventilator? If my patient is having trouble, let's say my patient's acidic, right? Not responding to Ringer's lactate, and they're on mechanical ventilator. Do you think I can have the technician start increasing the amount of times my patient breathes? Yep. You start increasing the respiratory rate, it moves them back here. Now, let's say the exact opposite happens. My patient's basic, 8 or 9. What's going to happen? I can have them relax and slow their breathing to where? They start slowing down, they start calming down, so they can get back where? Here. One situation is, let's say somebody's hyperventilating. You're hyperventilating, you're throwing out way too much acid, so you're going to be around here. But so what happens when you slow down and you calm down, or let's say you had a panic attack and you have to slow down and calm down, what's going to happen? Your breathing's going to slow down, and then it's going to bring, oopsies, it's going to bring your pH back to normal. Okay? So that's just a little, those are the two compensatory mechanisms for your pH on how your body has homeostasis and keeps in the middle. Buffers are chemical, and respiratory compensation is your lungs, of course. All right, that's a nice example. Let's now go to coenzymes and cofactors. You see the substrate and enzyme, right? The enzyme's already helping things, but there's things called coenzymes that even help things even more, and cofactors that help things even more. And good examples are vitamins. Now, here's the thing about vitamins. Coenzymes, cofactors. Co means they have to be together. And remember, we talked about this when I talked about this graph regarding enzymes. reactants. Did I say that we should just eat chemicals all day? Your body likes to metabolize things. So the reactants should be food. And the coenzymes and the cofactors, also known as your vitamins, when you take vitamin supplements, they should be supplementing the food. Or you should be eating foods that are rich in these cofactors or vitamins, because it's a better way. And how do we know medically, and goes back to the discussion regarding evidence, right? On your discussions, how do we know? Because I can tell you for a fact that if a healthy person with healthy kidneys, healthy liver takes a multivitamin like Centrum, more than 99% of it will end up in the toilet. If you're just taking it the crash diet and you're not taking it with food, or if you have no deficiencies, the majority of it will just end up in the toilet. And in medical school, that's what we do. Yes, vitamin D does bind with calcium. Ms. McGuire, you had a question specifically regarding vitamin D, or it was just a comment regarding how coenzymes, cofactors. I don't want to get into like how chemically it does it, but just know that, and it's a good advice, especially for your older patients, that you could take all the pills you want, but if it is not combined with a solid diet, these supplements will they won't really hurt you, but they will do nothing, and they're expensive for your patient. And that's why that's why when you look at even the word coenzyme, cofactor, if you're looking at something like co means it signals some sort of cooperation. And your body doesn't like chemicals, because if it did, we'd be living in a future where we just take meds and we don't have to eat food. But we as human beings have to eat food and have to process the food to get our energy. And this is the thing that I mentioned before as the basis of pharmacology. We can have inhibitor molecules to make the enzyme inactive, and we also could have molecules and chemicals that can make the enzyme even more active. But again, you start playing with the chemistry. I am not a fan of medication. It may seem ironic since I'm in internal medicine, but as a chemist, I was a chemist before I was a doctor. As a chemist, you, the human being, are the most complicated machine in the world. And adding more chemicals to an already complex mechanism makes things worse. It makes things dangerous, actually. Because I always advise against polypharmacy or multiple medications. Now, this stuff here, this is a little precursor for our digestive, so we're going to skip over that. Let's start looking at the next part, which is what is important to the human body. And these are called macromolecules. These are important to the human body. And biochemistry harps on these things. Now, carbohydrates are made out of carbons and hydrate, which is water. So it's made out of carbons, hydrogens, and oxygens. Proteins that can also be abbreviated as CHON, C-H-O-N, they're made out of carbons, hydrogens, oxygens, and nitrogens. Lipids are made out of carbons, hydrogens, oxygens. Do you see a pattern here? There's not much. It's very, very basic formula of who we are as human beings. Maybe if you watch a sci-fi channel, sometimes they call human beings carbon molecules, because all we are is carbon, like here, and water. And that's what a carbohydrate is. And nucleic acids are special because DNA and RNA are essentially the blueprint and the messenger of that blueprint of who you are as a human being. And we're going to talk more about DNA next week when we talk about protein synthesis and we talk about how your DNA, the blueprint of who you are, is actually the very precursor and the basis of all pathology. Because remember, we looked at that picture. We looked at atoms, molecules. Atoms make molecules. Molecules make macromolecules. Macromolecules make cells. Well, who do you think tells the atoms which way they should be forming to make what macromolecule? It's the nucleic acids. So, for example, if you're going to have heart disease, it's in your DNA. Somewhere in the genetic code, there's a code in there for you to have a predisposition for heart disease. But if those of you who studied biology know that there's nature and there's the nurture model. Unfortunately, genetics and medical science lean more towards the nature model. Even now, the American Psychiatric Association has already proven that many pathologic behaviors are inherited. There are gene loci or gene locations where they're linked to certain things. And we already known that with diabetes, but now things like alcoholism, drug abuse, spousal abuse, criminality, there is now a not definitive, but there's a decent link to your genetics. Now, you also have the nurture side of it. For example, my son is, he's not the kindest of kids. Well, he wasn't the kindest of kids. He's a kid who likes to fight. And when he was younger, what did I nurture? I nurtured that aspect because, you know, I wanted a warrior. I wanted a fighter. So I made him hyper aggressive when he was a kid. All right. So what did it do? Got fighting. He got kicked out of school. So instead of nurturing other things and maybe putting that aggression to other things, right? It actually halted his growth as a human being, right? But then so what did we do? When he got kicked out of school, we had mandatory counseling. And that's when we started realizing we're nurturing all the wrong things. So we started nurturing him in sports and nurturing him in workouts. So it's a way that he can project all that pent up energy instead of fighting. And, you know, I got him more away from training for fighting, but training for soccer or baseball or other things. But then when you look at it, is it any wonder that he became a Marine? Is it any wonder that I became a Marine? Is it any wonder that almost half of the Grias males are soldiers, right? And especially now, we don't need to be. My father and my uncles came to the United States because they needed a green card. I don't need a green card. I could have got loans. My son could have got loans just like everybody else. But you could see not only there's a genetic component, there's also a nurture component. Which side did you nurture, right? Or what thing did you nurture? And that can also be seen with drug abuse. If you look at coping skills of drug abuse patients, they were trained and taught negative ways to cope. And then they let the drugs take over, and then it becomes a chemical problem. So you can see here how DNA and the blueprint of who you are says a lot, but there's also a nurturing component of things. Now let's break these things down and let's look at each one of them. So carbohydrates. We talked about how there's a biological process of taking the food that we eat and then breaking it down into the energy that we need and breaking it down into your monosaccharide, which is a simple sugar. And the simplest of all the sugars is a 6-carbon sugar called glucose. Glucose is the basis for all metabolic fuel. And everything we eat can be broken, all the carbohydrates of food we eat. So you could see how glucose, a carbohydrate, is necessary. That's why I'm not a fan of anything that favors or removes any of these molecules on this list. So if you're looking at these fad diets, oh, you got to only do proteins, or you got to do only carbohydrates or only lipids at 3 p.m. in the afternoon. No, that's not how it works. You need all three, but you need it in, and I'm a true proponent of portion control. We as human beings eat way more than we need, especially those of us in the healthcare field that lead a relatively sedentary lifestyle. We're not in, we're not in the forest chopping down trees or jumping out of airplanes that requires massive amounts of energy. So why do we eat so much? I always tell the story. A couple of years ago, me and Dr. What was his name? Dr. Matra, he was a statistics professor, and he lost a lot of weight just by walking. And I always have trouble losing weight. And he and I had a challenge. He said, he asked me, he goes, just for a week, just eat whatever you want and see how many calories you eat in a day. And according to our resident dietitian, I remember it was Dr. Lee. She teaches dietetics for all the culinary baking and pastry. She says statistically, human being doesn't need more than 1,000 to 1,500 calories per day. Well, long story short, me and Dr. Matra, when we looked at what we were eating a day without dieting and just living a normal life, it was close to 6,000 calories a day. Six, almost seven. Because think about it, if you eat a Big Mac and a Big Mac meal, that's like 3,000, 3,500 calories. Now I got it down to like 2,000. I'm trying to keep it down to 2,000. But again, we're the only animal on the planet that eats more than what we need. And that leads to obesity and leads to problems. Because remember, I really wouldn't care less how we all look. That's the last thing on my mind. It's more about the balance of these things. And if you have way too many lipids versus proteins versus carbohydrates, that is that's a formula for pathology. That's a formula to get sick. And cellular respiration is really important because it's the biological process where these carbohydrates get broken down so I can get glucose and oxygen, hence the term respiration. Respiration is simply the exchange between oxygen and carbon dioxide. We breathe in oxygen and we exhale carbon dioxide. And the cells also breathe in oxygen and release carbon dioxide. And that is very important. And we need carbohydrates for that. And we definitely need glucose for that. Now you have monosaccharides, disaccharides, and oligosaccharides. They're just and polysaccharides. They're just categories of simple sugars to more complex sugars. And the more complex the sugar is, the harder it is to break down. That's why instead of eating, the snacks that we all usually love that have complex monosaccharides or polysaccharides, a lot of the food additives and preservatives are made out of polysaccharides, and they're not really good for you. But when you look at glucose and fructose, fructose is natural fruit sugar, right? If you just eat fruits, and me, I'm trying to be a fruit person. But before, when I used to be a drinker, the only time I have fruit is if it's mixed with rum. And it was just very strange for me, especially the other morning. I actually ate a melon for lunch, which was weird. But it's good because why? It's better than having something with starches and cellulose and all these polysaccharides, they're complex, which take way more energy and way more time to break down versus glucose and fructose. Now, now that I'm eating less, I'm feeling lighter. It's easier to wake up. It's easier to go to sleep. It's easier to do a lot of things. And the weight loss comes right after. I'm not a proponent of one of these people who you're constantly looking at your weight, because your weight fluctuates. It goes up and down, especially regarding your water intake. And that depresses patients. And we were always trying to keep our patients motivated and positive so they can stay compliant with the diet and stay compliant with their meds. Proteins. are essentially carbohydrates with a nitrogen. Hence, their abbreviation or slang, CHON, CHON. Now, proteins are made up of little amino acids. The amino acids get strung along together, and they're connected together by something called a peptide bond. And all the excess nitrogens get released in our urine and in our feces. Lipids. Now, lipids, you're gonna need a little bit of fat in your life. And lipids are good. But again, and they're just like carbohydrates, and carbohydrates turn into lipids very easy. And the function of the lipid is to store glucose. And that's why we look at phospholipids and triglycerides as a medical, when we take your blood, as a medical indication on how much fats and how much lipids you have in your body. And again, it has to be a balance. You can't have no lipids in your system, especially you ladies. Ladies, do not believe the hype of the media and the TV. You're not supposed to be that thin. When I look at athletes and when I look at people in the media, there's way too many skinny people on TV, and they're not really that skinny in real life. I used to be a production assistant for a movie house in New York City, and I've seen all these artists up close and in real life. They're not as pretty, they're not as thin, and there's a lot of editing that is done. I have a cousin who works for Saatchi & Saatchi. He's an art director. He informs me that all of their images, even of their best models, are photoshopped. So what was the purpose of having the model in the first place? Well, it makes everyone insecure. And ladies, guess what your normal body fat is for a normal woman? 18 to 20%. So you're supposed to be a little bit, and yes, Ms. McGuire, totally. Thank you for mentioning that. Your fat has estrogen. It goes is part of a cycle that creates estrogen. So a lot of these athletes, my sister used to be not really thin, but she used to be an athlete in high school and in college. Heck, she almost barely got her period because she works out 6 to 7 days a week. She was down to like 7% body fat. And then, so what did it do to her menstrual cycle? She had dysmenorrhea from the age 14 all the way until she stopped training when she was, when she blew out her knee. She was 20. And then, unfortunately, she was playing for Columbia University. She was playing field hockey. She was on a half scholarship, blew out her knee, and that was it. That was done. So then she had to pay in full. And that's how Dr. Garias got to go to the Marine Corps, because we ran out of money. Classic story. Now, fats. They're saturated or unsaturated. And again, a lot of people say, oh, you only eat saturated or unsaturated fats. Again, it's also part of a portion control. But fats that are unsaturated have double bonds, and they're generally liquid at room temperature. Now, it's never a good idea to eat anything that is in oil that is solid at room temperature. But the problem is, it tastes fabulous. Have you guys ever had old school popcorn that was cooked in coconut oil? I used to work for a movie theater in the early 80s, and it was just nasty stuff back there. But the popcorn tasted fabulous. Why? Because it's very fatty, and it's very, very tasty. By the way, we have in our, and I'll go over it in greater detail in Anatomy and Physiology 2. Do you know how they say that people have a sweet tooth? We have a sweet tooth. In our tongue, we have sensors called glucostats. And the glucostat is our sweet tooth. Some people have more of them than others. And those are the people who love sugar. Guess what else we have in our tongues. We also have lipostats. It's the reason why when I eat baked Doritos, it tastes like garbage. But when I eat normal Doritos, it tastes awesome. Because what is my tongue and my sensory really looking for? It's looking for the fat. Ask Chef Nori Hathaway. She heads up culinary baking and pastry. When every time we applaud her and her chefs, she always says it's all about the sugar, it's all about the fat, and it's true. It's the reason why we all love takeout so much. And of course, nucleic acids, DNA, and RNA. RNA is kind of like the messenger to translate and propagate the code that's in DNA. For right now, the only thing you need to know about DNA is that it's the genetic code. It's a code that has everything about you. It knows when you're going to be born. It knows when you're going to die. It gives odds are if you can have kids, don't have kids, how many kids. Just know that it's the everything of who you are, including disease. And that's why we're so interested in genetics, not because a lot of people get scared because they're like, oh, you want to create a perfect human race like Hitler. No, we don't. We just want to get into the DNA code to find, let's say, for example, I have a DNA and genetics for heart disease. Wouldn't it be really great if I can find that part of my DNA and remove it so that I won't have heart disease? Or if someone has cancer, unfortunately, the women in in the Garais family, they are predisposed to breast cancer and cervical, right? So when my sister had an abnormal pap smear, what'd she do? She panicked, right? But then she calmed down, and then what? Now she's constantly monitoring her pap smear, which is the right thing to do, and then also constantly looking at her health and changing the way she lives so that she'll be less disposed to cervical cancer. And that's really what we do. We medically manage our patients. We don't really cure anybody or solve any, we solve a lot of problems, but we don't really, what do you call that? Save people. I was watching this thing last night, this doctor, like, how we're saving people from COVID. No one's saving anyone. No one's saving anyone from anything. As far as I know, there's no vaccine. There is the only medical management for a virus is what? Write it out and just take care of your patient's medical needs and their immune system while they're writing it out, right? So, like, who did you save? It's a little bit arrogant to say, oh, I saved somebody. I get kind of weirded out when people say stuff like that. So we already talked about basic chemical structures in organisms. We talked about the biochemical macromolecules. Let's talk about bonding. And I could show you bonding in picture and a chart. It'll be easier to look at it. Where's images? Here you go. Couldn't find images. Hey, look. I usually find this chart that has oh, by the way, regarding concept maps, you can Google and look up concept maps, and you could do it on Microsoft Word. And this is actually what a concept map is. It's actually how does all these ideas connect with each other. And it's a better way of studying versus just writing notes, right? It's a way to show relationships, and also it can show your notes in a visual form. Most people are not auditory learners, okay? That's why I record my sessions, so you can hear it over and over and over again. We're visual learners, so it's easier to kind of close your eyes and look at arrows and see where things go. And because you need this stuff not only for this midterm. You ace my midterm, honestly, I really wouldn't care less. You ace my final, you ace this course, really would care less. What's important to me as an educator is when you become a nurse or you become a doctor or a technician or anything in the medical field after you graduate, that you actually know how to apply these things. Okay. Those of you who've ever worked in a hospital know around April, May, you have all these doctors, brand new doctors. They know so much, but they don't know how to do squat. And it's scary. That's why I always make the joke. Well, it's not really a joke. It's kind of like advice. If you're really, really sick, try not to be in a teaching hospital around the months of April. It's not a good idea. Yes, someone has a comment? No? Yes? Hello? No? I make that joke, but I remember my as a first year resident, even though I have a lot of I had years of being a medical assistant, years of being also I was in EMS for 2 years. It's still, you know, it only roughly prepared me uh, to be a physician, to be a doctor, and to actually be the go-to person, right? That takes time, that takes experience, and that's why we have residency programs. So that's actually the more important thing you guys should be focusing on. You should be asking yourself, can I get this stuff in my long-term memory so that years from now, right, months from now, years from now, that it'll stick with me forever, so I don't have to relearn it. There's also a reason why your continuing medical education is like every month, because it's always constantly updating. So let me get the bonds. Chemical. It's gotta, I'm looking for this thing I used to always post. If I can't find it here, I should always save these things. I'm always trying to rely on my memory, which is not a good thing. Here's a nice example. Okay. Now, what are bonds? These are atoms. They're two hydrogen atoms. And if you look at here, they're sharing. And here's a double bond, and they're also sharing. So when they share, that's called a covalent bond. Again, back to the medical term co, right? Now, another example of bonds is ionic. Now, ionic bonds, we already looked at ions already. We looked at H plus, which is anything with a charge like H plus and OH minus. That's an ion. And if you saw here, the covalent bond, they share their electrons. But if you look at an ionic bond, they kind of borrow it. Okay? Now, the covalent bond, it could be like this H2, it could be an even sharing, but it also could be uneven. But clearly, ionic bonds, they occur when something like this, like for example, chloride has one extra electron. So if it has one extra electron, it's a minus. So Cl minus. Let me see if I can make this bigger. There you go. And sodium has one less electron, so that's an Na plus. Now you see the plus is going to get attracted to the minus, and it's going to form a bond, or it's going to form a relationship. Okay? So covalent bond, they share. Ionic bonds, they kind of borrow. Okay? Now, another kind of bond deals with water. So let's look at the study guide for water. So we already went through ionic bonds. The plus is a cation, and the negatively charged is an anion. So in sodium chloride, which is an example of an ionic bond, sodium is the cation and the anion is chloride. Now, covalent bond, we already talked about one that shares evenly, nonpolar, versus one that shares unevenly, polar. Now, how do the electrons attract each other? They attract each other due to this physical property called electronegativity. If something's very electronegative, right, it can now share via covalent bonds. And think sharing covalent bonds. Now, because of these bonds, and because of water has a really interesting property, right? We can make a solution, we can make a mixture. And there's three types of mixtures: suspensions, colloids, and solutions. And they're distinguished from each other, these mixtures, on their physical property. So, for example, a suspension is heterogeneous, meaning is that it's not really separated into two parts. And it's like when you put like, you know, when you like make a salad and you put some herbs and oil for your vinaigrette, you could see like the little bits and pieces of the pepper and the paprika and whatnot all floating around. And there are some medications that are in suspension. And knowing and understanding that, how many times have I erroneously almost gave a suspension without shaking it first, right? So it has a little, so because you have to shake it because stuff is going to end up in the bottom. Now, a solution is when you make, you have the powder portion, right, which is called the solute, and then the water portion, which is called the solvent. You put them together, and then once you mix them together, you can't take it apart by any normal means. So you don't have to shake that particular medication because it's already it's already mixed well. And the ability to mix well is called solubility. Some things are soluble in water. Some things are soluble in fat. Other things are soluble in alcohol, right? And then whatever is soluble in water is insoluble in fat. So if something's water soluble, like a drug that's water soluble, if I try to inject that in a part of your body that's fatty, it's just going to get dispersed. Solvent, solute, aqueous. Now, saturated or unsaturated. What is a saturated solution? This is how I think, this is how I look at solutions. The easy way to look at things is the things that you already know. And an example is like Kool-Aid. Everyone here has made Kool-Aid. So you have like the powder portion, which is the solute right here. And then the solvent, which in the case of Kool-Aid or any mixed drink is aqueous. And then when you mix it all together, it forms Kool-Aid. But if you make Kool-Aid the way I make Kool-Aid, I use way too much sugar, way too much Kool-Aid powder. So then you have a saturated solution. So no matter how many times I stir, what is going to be at the bottom of the pitcher? You're going to have powder because there's not enough water molecules to match up with the solute, which is the sugar and the Kool-Aid mix. Okay. Now, there are some things that are hydrophilic. Philic means loving. So there are some things that are water soluble. So they love, right, water. And there's things that are hydrophobic, like oil. If you put vegetable oil and water together in a bottle, you shake it up, what's eventually going to happen? They're going to separate into two different layers. And that's called, that property is hydrophobic. So this answers the question in your body. Didn't you ever wonder how do certain things end up in certain places? And why does certain things in your body stay in one place and don't move around? I used to always wonder that, like, how is it when I drink water that it doesn't just it goes down my stomach. Why it doesn't just, you know, just spread out or just dissolves? Well, it just doesn't, because like dissolves like. And there's hydrophilic portions of our body which will take in water, like our large intestine. And there's hydrophobic sections of our body that will start throwing out water. And one of those places is your kidney. Let's now show the other bond that I was getting to. Let's talk about hydrogen bonds. Hydrogen bonds, and the great example is water. If we look at water, it's made out of two hydrogens, as you can see here, connected to an oxygen. Hence the term H2, because there's two of them, O. Now, you'll see it automatically forms a positive side, and this delta here is a Greek alphabet. Delta plus is partial positive and a partial negative. And then when we put that all together with other water molecules, it forms the partial positive part of the hydrogen ion attracts to the partial negative part of the oxygen ion, and it forms a weak bond called a hydrogen bond. Now remember that it's weak and it's flimsy. That means it can bend. Remember that for next week's lecture when we talk about DNA. Hint, DNA has all this millions and millions, and actually billions, trillions of pieces of information. How does it fit on something smaller than a cell? Well, part of the key is it folds. And the way it folds is because it has lots of hydrogen bonds. Okay, and also, doesn't it make sense now why we're 2/3 water? And now you could see how also, if I put a whole bunch of hydrogen bonds, right? I make water, right? This is H2O, and then I put in salt. I didn't make salt disappear. The sodium part got attracted to the partial negative. The chloride part, which is negative, got attracted to the partial positive. It pulled away the sodium from the chloride. The ionic bond got dispersed. And now we have salt inside water. And it could be also removed as well. And that's called a saline solution, which is, guess what you're made out of? 0.9% sodium chloride solution, also known as NSS, or normal saline, which is human beings at a pH at around 7.4. So with that being said, let's look at all the things we know. We went over some bonds, and watch the video. There's even more bonds, but there's also a PowerPoint on the next lesson to show you. We went over macromolecules, basic chemical structures, and water. Now, what is due next week? Look up on how to design a concept map, and you could do it on Microsoft Word. So let's say, for example, I talked about, let me get rid of this. Can I just do this? Like, what was the first thing I talked about? Let's say I insert, and then you just have a shape. And let's start with this circle. And I talked about bonds. So I could type inside here and bonds. And then I could have little circles and shapes here, here. And then let's say I talked about ionic bonds. And then I talked about hydrogen bonds. Make this a little bigger so it can fit. And then can I insert and draw an arrow? Yep. Draw another arrow. Oopsies. Didn't mean to do that. So you could see here, you just play around with it. Or another thing you could do just take a scrap piece of paper, do it neatly with like a stencil, like a coin, make a round circle and a ruler, and print legibly. And then do you think you could scan that or take a picture? And then you could talk about what about ionic bonds is important? What about H bonds are important? And then how do bonds relate to the other chemical stuff? And then you could see how you could build it there. Okay. And if you need also further help with that, give me a call, and we could set up a Zoom session tomorrow or later in the week, or maybe, well, not today, I'm full up. I have to go to campus after this, and then I got meetings, and then I have tutoring at 4. But there's also YouTube and things of that matter. Try those outlets first, and then if those aren't helping you, give me a call, and then we could do a Zoom session. Now, that is what's due for task 2. Discussion 2. Now, based on now you could look up the case study, or and there's an application question on Alzheimer's disease. Let me show you where that thing is. If you look at lesson 2, there's a PowerPoint. I believe it's here. And if you download the case, there's a PowerPoint here. And you know what? I will make the case available. I'll make the PowerPoint available on your announcements. But if you, and you could go through this PowerPoint, it's nice. And it also goes through the different kind of bonds and kind of stuff that I went over. But you look at the very last slide, practical application. This is the case study. Okay. Remember, so for the discussion, you read this, and it talks about beta amyloid plaques in the brain, which cause the dementia symptoms for Alzheimer's. And dementia is progressive memory loss, and it's profound. Meaning to say is like you'll forget how to eat, you'll forget how to, and it's progressive. It starts out slow, like you forgot, an address that you've known for years. A good friend of the family, actually my mother's lab partner in medical school, she had a practice of 15 years in the same place in San Diego. And one day she couldn't remember how to get to it. She called her assistant, said, call me an ambulance, there's something wrong. And then over the months, she started forgetting everything. And then I visited her. She thought I was one of her residents. I thought I was her favorite nephew, but apparently she thought I was a resident. And then she started quizzing me as if I was a resident. It was kind of sad. And it was awful because she had 2 daughters. She didn't remember her daughters, but she remembered me because I was in a white coat. Well, not me, but what she thought was one of her residents. So for lesson 2, don't go over these labs. You can look up starch test, protein test, and fat test. Actually, I suggest you do. What's a starch test? What's a protein test? What's a test for fat? Now, so in the same case study, so you're going to use this case study. That part was for, that one part for Alzheimer's is for discussion 2. Now, what will you need to answer the questions? Well, when you look through this, where is one? There's questions all throughout, see? CQ question number 1. Just on a Microsoft Word document, just write your name and the date and write CQ1. What's the answer, right? And then you go to the next one, CQ2, what's the answer? Okay? And so, and I believe there's like 10 or 11 questions. Okay? So that's what the lesson. So to recap, what's due for next week? 1, your concept map of today's lecture for those 4 topics. The discussion on Alzheimer's and beta amyloid based on that, that paragraph, this last paragraph here, that's in that PowerPoint. Okay. And remember, 200 words, have in your own words, and discuss the link between beta amyloid and have some evidence. Where'd you get it from? Okay. And also make a comment on, is this the current diagnosis criteria for Alzheimer's disease? Okay. And then last but not least, answer all the questions 1 through 11, CQ 11, right? CQ 8, blah, 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 blah. Okay. And put that in a Microsoft Word document. All right. That is week 2. Let me see any questions. And the homework again. So of course the task, which is, let's go back. So 3 things, just like every week. Task 2, concept map of today's lecture. So it's concept map of these 4 topics, which is essentially today's lecture. Discussion 2, which is due next week as well, before the next class session. And that will take what was inside that PowerPoint, look at the case study, and answer the application question regarding beta amyloid, the relationship with beta amyloid and Alzheimer's disease. Okay, at least 200 words, and make sure you cite your source, and you cite your source properly. And last but not least, for lesson 2, all 11 questions that are embedded within the PowerPoint, and I will make the PowerPoint available so it'll be easier for everyone to access it. I'll put it right here in announcements. Let's go week 2 PowerPoint to be utilized for 1, discussion on Alzheimer's. And 2, let me fix this. CQ questions due for lesson 2, CQ number 1 through CQ number 11. And let's put that bad boy in there. Post with no delay, so you can access it immediately. Boom. And of course, I will have today's lecture as well. Anybody else have any questions?
Thanks for the lecture.
You're welcome. Have a good one, everyone. And
thank you.
If you're missing any week 1 stuff, please get it in today. I won't be grading. I won't be looking at it until later. All right.
Thank you.
Have a good one.